Now we'll define conditional expectation. Conditional expectation leads to the definition of, leads to actually a theorem which is the total expectation theorem, which is useful. And will solve a number of interesting problems using this. Okay, so let x and y be defined as, random variables defined on the same probability space. And let A be an event, again, on this probability space with probability different from 0. The expected value of x given A. How would you define this? I mean, you know the definition of expectation. Okay. Now, conditional expectation. What do we know? We know that the event A happened. We know then the conditional PMF of x given A happened. Now we need to compute the expected value or the mean of x under this condition. So it makes complete sense to define the expected value of x given A as all values x weighed by the probability of these values under the condition x. What is that? P x given A, x given A, the conditional PMF, summed. Okay. Yes, please.
To make sense,
right, but when I write it like this, suppose there's a value of x which is impossible under the event A. That will be taken care of by this, which will be 0 in that case. So this expression is completely valid and it's general. Okay. Of course, as Emre pointed out, it's a correct observation. The only non-zero terms in this summation are those that are possible under the event A. In other words, those that have a positive probability mass condition on A. Okay? So I think enough said about this. Now, natural extension. We can compute the expectation of a function of x under the condition A. So expectation of g of x given A. Would anyone volunteer to give an answer to this? Do you remember that we had earlier the expected value of a function of a random variable is summation over all values that the random variable can take, g of x, px of x. Okay? The only thing that changes here is the conditioning. So summation over all x, g of x, px given A. Is this okay? Makes sense, right? What's next? Expected value of x given y equals y. Conditioning on the value that the random variable y takes. But this is an event. Y equals y is an event. And this is nothing but this, okay? You can think of y equals y as an event A. So this is summation over all x times px given y equals y. But we already have a name for that. That's the conditional PMF of x conditional on y. So x given y equals y. Okay? Please look at this very carefully and tell me if there's anything that's bothering you about this. All right, we can extend the expectation definition. We can extend the total probability theorem to expectations. How do we do that? Suppose we're trying to compute the expectation of a random variable x. Okay. Let's take a disjoint partition of the sample space, A1, A2, A3, up to AN. Okay. Now, this equation tells us that, this equality tells us that expected value of x can be computed by taking the expected value of x conditioned on the event AI, multiplying by the probability of AI, and summing this over all I. Why is this true? Why is this true? Why do you think this is true? How about, as in everything, all we need to do is to write the definition of expectation. Expected value of x, at least tell me this, summation x times px of x. Now, this is a probability, right? So I can expand this using the total probability theorem in terms of the AIs. Summation p x given AI times probability of AI over all i's for the fixed x. Rewrite this double summation x summation over I p x given AI p of AI. Any problem so far? Okay, what do? We can change the order of summations if you want. Summation over all I, summation over all x. Maybe also take this and move it to the outside of the x summation, p of AI, summation over all x, x times px given AI, x given AI. Now what do you see here? What do you see here? This expected value of x given AI. So we're done. We're done computing, we're done showing that you can find the expectation of x using this expression, which is known as the total expectation theorem. Let's write it. We don't have to write it, it's already written here. Total expectation theorem. Okay? It just tells you that in order to compute the expected value of a random variable, you can divide the sample space into disjoint parts. You can make a partition, compute the expectation on each partition, and then take a weighted sum of the expectations, which makes life very easy in a lot of problems. Here's another version of the total expectation theorem. Now I'm applying the total expectation theorem to a conditional expectation. Please watch very closely. Expected value of x given b. It's an expectation. It's actually a conditional expectation. I can compute this using the total expectation theorem. What do I have to do? I need to condition on events AI and multiply by the probabilities of these AIs. But these probabilities now have to be conditional probabilities because I'm already in the conditional environment. I'm already in the new universe, which is the event B. Okay? Do you have any doubts about deriving this? Now, when AI and B are both in the conditioning, AI happened and BI happened, that corresponds to the intersection of AI and B being in the conditioning. Okay? A lot of people make this mistake very frequently. When they are using this, they forget to keep B in the conditioning. Of course, you have to keep B in the conditioning because it's in the conditioning to begin with. B has happened. Okay? There's no way of going back. B has happened, so B is in the conditioning. Okay, what's next? Again, I can apply the total expectation theorem by letting the event AI be y equals y. Okay, the event AI is the event that the random variable y takes on a certain value. Okay, so of course they are disjoint and of course they are a partition. So expected value of x can be written as py of y expected x given y equals y. Okay, I would like you to make sure all of these seem very straightforward to you. Okay, so read them and try to derive them and understand them until you know them like the back of your hand. Okay, and let's just, put a concrete example on the board so that this all means something to us. How can we make something like this useful? Okay, here's an example. There's a router, okay, an internet router or switch. Data flows entering a router are low-rate flows with probability 0.7. What's a low-rate flow? Let's talk about networks a little bit. Like when somebody is, for example, doing a chat or sending messages, or that's a quite low-rate flow. Or downloading a file, that could be low rate. On the other hand, when somebody is watching something on YouTube, right? Video transmission, that's higher rate. Okay. Sometimes, so in the internet, there are high rates and low rate flows, and somehow routers have to serve all of these. Okay. Somehow they have to find a way of fairly sharing the bandwidth between these flows. Anyway. This example is about that. So roughly 70% of all flows are low rate, and 30% of all flows are high rate. That's represented by the probability of any flow having a high rate being 0.3. Low rate sessions have a mean rate of 10 kilobits per second. High rate sessions have a rate of 200 kilobits per second. They're not that high after all. What is the mean rate entering the router? Mean rate, in other words, expected rate. So, the flow rate R is high with probability 0.3 and low with probability 0.7. And R is random. It's a random variable. The expected value of R is, using the total probability theorem, the expected value of R given high rate times the probability of a high rate flow, 0.3, plus the expected value of the rate, given it's a low rate flow, times 0.7. Okay? Expected value of the rate, given that it's a high rate flow, is 200. Expected value of the rate, given it's a low rate flow, is just 10. So this comes out to be 67 kilobits per second, mean bits or bytes? Mean rate. So on average, this is the rate that the router sees. Any question? Okay, I guess this is a simple example. Let's do another example which could illustrate these things even better on a PMF, joint PMF. Because this example was kind of implicit. The next one is more explicit. And I think the next one really shows you the usefulness of the total expectation theorem. Okay, so x and y, x and y are between 1 and 6. Okay, so 1, 2, 3, 4, 5, 6. Similarly, again, 1, 2, 3, 4, 5, and 6. Okay, what is this? The plot of the joint PMF. The joint PMF. So there are two regions obviously here. X and Y are both between 4 and 6. That's one region of 9 points. Let me try to do my best showing that region. Oops. Okay, so these 9 points. What is the probability mass at each of these points? 1 over 27. And there are 9 other points. X and Y are between 1 and 3. So okay? And the masses, the probability masses here are 2 over 27. Does this add to 1? Why? Because 2 over 7, 27 times 9, which is 2 over 3 plus 1 over 3. Okay, no problem. Now, it says find the expectation of x. Now, before this hour, if somebody gave you this and said find the expectation of x, how would you do it? You would have to compute the marginal PMF of x. What is the probability that x is 1? What is the probability that x is 2? What is the probability that x is 3? What is the probability that x is 4, etc. And then you would take a summation, x times probability that x is x. Okay, that's a long way of doing this problem. A clever way of doing this problem is to realize here that there are two regions. This is region A, this is region B. Or A and A complement if you want. Okay? And you can apply the total expectation theorem. The expected value of x is expected value of x given x is in A times the probability of A plus the expected value of x given x is in B times the probability of B. Why? Because A and B are a partition. Okay. Now, let's use again our intuition. Let's do this by inspection. What is the expected value of x given x is in A? Huh? A. A is this. This is x and this is y. Now, if we are in A, by total symmetry, the center of the PMF is 5. So the expectation of x is 5. What is the probability of A? Well, the ratio of 1, the probability of A to B is 1 to 2. So 1/3 should be the probability of A. Okay? Plus expected value of x given B. Well, if we are in B, x is expected to be 2. 2. What is the probability that we are in B? B is B is twice as likely as A, so the probability of B is 2/3. 2/3. Any questions? This comes out to be 3, by the way. So it's the center of the whole range is 3.5. The expectation of x is slightly shifted to the left, which is because of the higher probability masses on the red dots. The red dots are heavier. The black dots are lighter. So that shifts the center of gravity to the left. What is the center of gravity from, what is the y coordinate of the center of gravity? Huh? What? Again 3? Okay. So the center of gravity is right here. Any questions? Yes, please. Okay. So these points all have mass 1/27. These points all have mass 2/27. There are 9 points here. We add 9 of them to get the probability, which actually gives us 9 times 1/27, which is 1/3. But logically, since each point here is half as likely as each point here, this whole thing is half as likely as this. Together, they add to 1. So it has to be 1/3, 2/3.
Hocam sola kaydetmişsiniz.
What?
Yani mesela 1/27 olsaydı B tarafındaki
Of course, that wouldn't be 27 though. We need to renormalize. So your question is, what if the black dots and the red dots have the same masses? There are 18 dots, so 1/18 would be the probability mass at each point, 1/18, right? And then the center would be right at 3.5. Questions? Comments? Yes.
Böyle karmaşık bir şekilde olsaydı, bunun gibi simetrik olmasaydı, o zaman da parçaları kümeleri bölüp de simetrik şeyler oluşturup yapabilir miydik? Aynı şekilde.
Right. I mean, by the way, there's nothing special about all of these things having the same probability. So even if these have different probabilities, like 1/27, 2/27, 0, okay, and 3/27, 0, 0, okay. Again, this is region A and it's valid, and we can compute the probability of region A. See, it's not even a square anymore. Our region includes this, and this. It's an irregularly shaped region, but I can compute the P of A by summing these values. Now, what's a little more difficult is given that I am in this region, what is the expectation of x? Now, in this example, it's not 5 anymore. Okay? So if computing the expectation given A is, difficult, then using the total expectation theorem will not make things so much more simpler than directly computing the expectation. So you decide. You have this as a tool, and as a problem solver, you see, you look to see if you have any structure in the problem. If the problem has nice structure, then you can apply the total expectation theorem, and it will buy you some time. Okay. Any other questions? You should be doing more examples. From your questions, I sense that though these examples are the only examples you see, which is not contributing to your understanding. Okay, you really should be doing examples which will make everything more fun and easier to learn. Probability, learning probability is really about getting used to the models and the notation. Okay, after all, why are you learning this material? You're learning this material in order to apply it in some fields in the future. Okay, in the near future, you'll apply it in stochastic signal processing. Okay, in EE306. Afterwards, if you go into networks, which I'm working on, which heavily uses probability, you'll apply it in networks. Or if you go to, if you're into physics, statistical mechanics, etc., you will use it there. Or if you go into economics or finance, again, everything will be based on probability. And probability is really a tool in order to model uncertain situations and get, answers about the behavior of systems. Okay, so you should be doing problems, solving problems. And in the book, there are really a lot of good, well-designed problems. Their answers are also available on the website of the book, in case you didn't know. Okay, so let me repeat. The solutions of the problems in the book are available on the internet. Okay, so no reason to not do them. Okay, let's do a final example. 3 rolls of a die. 3 rolls of a fair die. Okay. We have 3 locations. Each location will be a number between 1 and 6, equally likely. Let x be the total number of 6s. So, x is the number of 6s, okay? And x takes a number between 0 to 3. 0, 1, 2, 3. Right? And y is the number of 1s. Y is the number of 1s. And y, again, lives between 0, 1, and 3. Okay. Find the joint PMF of x and y. Find the expectation of x given y and the expectation of x. Okay, let's start by finding the expectation of x given y. Expected value of x given y. What do you suggest? Well, expected value of x given y. What is this, by the way? What do we understand from this? We need to first understand this. Y is a random variable. So, is this a value? No. Okay? This is a function of y. Okay? This is a function of y. You see this? Because given y is not specified. Given y, so if you give me a value for y, this tells me the expectation of x. If you haven't given me anything, it's just left as a variable. So this is a function of y. This is a random variable. Okay? Expectation of x given y, if you have not specified y, is a random variable. Okay? So now let's compute it for different values of y. Expectation of y, x given y equals 0. I can do this. Now this is a number. Okay? If y is 0, what does this tell me? There are no 1s. So the numbers between 2 and 6 now are equally likely in each toss. You can show this. We already have shown things like this. I'm skipping over that. So how do we compute the expectation of x? Now, if y is 0, this tells me that the numbers will come from 2, 3, 4, 5, 6. And x is only carrying whether they are 6 or not. Okay? So, location I, let's call it L, L1, L2, L3. L1, okay, L1 is 1 if I get a 6. 6 occurs in toss 1 and 0 otherwise. Okay? What is the probability, conditional probability that L1 is 1 given that y is 0? Given that y is 0, the likelihood of a 6 is 1 over 5. Okay? 1 in 5. 1 in 5. The probability that L1 is 0 given y is 0 is then 4 in 5. Okay. And the same thing is true for L2 and L3. So I can just say this for all Li's, I in 1, 2, 3. Okay. What is the expectation of x? What is x? X is nothing but L1 plus L2 plus L3. Right? So the expected value of x is 3 times the expected value of L1. Expected value of x given y is summation expected Li given y equals 0, I from 1 to 3. Okay? So, Li is 1 with probability what? With probability? Li is 1 with probability 1 over 5. Okay, so what is the expectation? It's a Bernoulli random variable, so its expectation is equal to the probability that's 1, which is 1 over 5. So summation 1 over 5, I from 1 to 3. So what do we learn? This is 3 over 5. Given y equals 0, given that there are no 1s, the expected number of 6s is 3 over 5 in 3 tosses. Makes sense, right? No? Okay, let's repeat. There are 3 tosses. What is the expected number of 6s? Huh? 1/6 times 3. In every toss, you get a 6 with probability 1/6. You have 3 trials, so 3 times 1/6. Now, this is different. In every toss, you're guaranteed not to get a 1. So the chances of a 6 have increased to 1 in 5. You have 3 tosses, so 3/5. Okay? So that's the expected value of x given y equals 0. Okay? Ask questions if you're not following. That's okay. Are you totally cut off? No, you're not? Okay. Okay, so how about, let me ask you a simple question. Expected value of x given y equals 3. Who said 0? You said 0? Good. Okay. Why? Because all the tosses resulted in 1. We have no possibility for any 6s. How about the expected value of x given y is 1? Y is 1. One of them are set to be 1. We have only 2 locations left. And in each location, the probability of a 6 is 1 in 5. Right? Expected value then, 2/5. And finally, the expected value of the number of 6s given the number of 1s is 2 is 1 in 5. Okay. So now do you see that expected x given y is a function of y? Yes. Plot it with respect to y. So, expected value of x given y equals y as a function of y. When y is 0, it's 3/5. When y is 1, it's 2/5. When y is 2, it is 1/5. When y is 3, it's 0. Linearly decreasing, which makes sense. Huh? As the number of 1s increases, the number of 6s decrease. Okay? So, expected x given y is a function of y, and it's a random variable. Let me repeat. What are these? This is a PMF. I mean, just like a PMF, right? Expected value of x given y. Okay. Is a function of y. Okay. Now, if I'm not leaving y, okay. If y is left as a random variable, let me use this to compute the expected value of x. Expected value of x is expected value of x given y, py of y. Why is this true? This is the total expectation theorem. Okay? Now, I already know these values, and I already know the probability that y takes all of these values. So let me compute this. For y equals 0, let's start from y equals 0. Expected x given y equals 0 is 3/5. What is the probability that y is 0? Meaning there are no 1s. No one. So all the trials are different from 1. The probability of a trial is different from 1 is 5 over 6. 5 over 6 cubed. Right? Plus expected y, x given y equals 1. 2 over 5. What is the probability that there are 2 1s? This is like a binomial. In each trial, I get a 1 with probability 5 over 6. What is the probability that I get exactly 2 1s? 3 choose 2. 5 over 6 to the power 2 times 1 over 6. Wait. 5 over 6 to the power 1. Wait. 2 1s, right? So 5 over 6 is the probability of 1. And wait, I wrote the same thing again. 1 over 6 is the probability of a 1. And 5 over 6 is the probability of anything else. Okay? Plus, what is the expected value of x given y is 2? It's 1 over 5. What is the probability that y is 2? Meaning there are 2 1s. Okay. What am I doing here? I already did that, right? I already did that. Okay, so let me turn this, switch this back to 1. And now I'm doing 3 choose 2, 1 over 6 to the 2, 5 over 6. And finally, what is the probability that all 3 are 1s? Oh wait, I forgot the coefficient here. The coefficient was 1 over 5. The coefficient here is 0, so I don't have to compute it. But if you want, let me compute it. 5 over 6 to the power 3. Okay? So I computed the expectation of x using the total expectation theorem. This is also called iterated expectations. By the way, we'll revisit this next time. This is the expected value of x given y. Okay? So think about this problem and solve more problems. Do your homework.